In this video, we discuss the composite functions involving our inverse trig functions and the corresponding trigonometric functions. I just thought it was sort of an interesting question or an interesting comment that when you take the um, inverse function and you take its composite with the original function, you should always get y equals x, and you will always get y equals x, provided that the original function was 1-to-1. But if you take a composite function with a function in its inverse, and one of those functions was not 1-to-1, so you had to create a restriction of that original function in order to come up with a composition in the first place, then the result of that composition is not always x. It's always closely related to x, but it's not always x. So I thought we might explore that for our trig functions. I think it's kind of interesting. It makes some kind of cool curves that you'll see, or not curves really, it's just a lot of piecewise linear functions that you'll see when you study Fourier series, when you study partial differential equations, if you choose to take that class. But let's look at some functions that are 1-to-1 first. Here I've defined a function, y equals 5 times the quantity x minus 2 cubed plus 1. And I can always think of this function in terms of what has happened to x. So I took my x value, I subtracted 2 from it. After I subtracted 2 from it, then I cubed it, then I multiplied it by 5, and then I added 1. If I wanted to find the corresponding inverse function, I'm going to call that h of x. If I wanted to find the corresponding inverse function, basically what I would do is undo every operation that I just did, but in the opposite order. So the last thing that we did was we added 1 to that function. So the first thing that we want to do when we define the inverse function is subtract 1 from our x value. And then right before we added the 1, we multiplied by 5. So to undo that multiplication by 5, we would divide by 5. And then right before we multiplied by 5, we cubed something. So what we want to do now, in order to undo that cubing function, is we want to take the cube root or raise something to the 1/3 power. That's the same thing. And then the first thing that we did to x was we subtracted 2 from it. If we add 2, then we get the corresponding inverse function. We can see that this orange graph is 1-to-1. Every x value has only one y value, and every y value has only one x value. And the same is true for the purple graph. Every x value has only one y, and every y has only one x. We've got the symmetry across the line y equals x. If the point AB is on the graph of the purple function, the point BA is on the graph of the orange function. So if we take the composite f of, or h of g of x or g of h of x, we should just get x back, because all of those operations really do undo each other, and they just return x. So we see that if we compute h of g of x, we just get y equals x. And if we have Desmos compute g of h of x, we get y equals, or we just get an x back. We could do all of that on paper, but I won't emphasize that now. But that's the idea. When your functions are actually 1-to-1, when you take the composite function, you get x. But you might say, okay, but what about like arcsine or arctangent? Remember, arcsine and arctangent come from taking a couple of functions, like y equals sine of x, and then switching the roles of x and y. So if this is y equals sine of x, if I don't worry about sort of the desire to have an inverse function, but if I'm comfortable with an inverse relation, I can just switch x and y. Instead of having y equals sine of x, I can have x equals sine of y. And we get that graph. So we can imagine just taking that sine graph, and instead of graphing it along the x-axis, we graph it along the y-axis. And we have to remember that as x increases, y is supposed to increase with that sine function. We start at 0, then we go to the maximum of 1, and then we go back to 0, and then we go to the minimum of -1, and then back to 0. We want to do the same thing when we're graphing x as a function of y, except you remember that y is increasing as you go upward rather than going downward. So if I were to just turn my paper sideways and then start graphing, my graph would be flipped. It would be wrong. So what I need to do is think about taking that sine graph and then graphing it on the positive y-axis like this, as opposed to graphing it on the negative y-axis, which would be our habit because we have a tendency to have that, that region where x and y are both positive in that top right corner. So instead of doing it in the top right corner, we need it to be in the top left corner in order to graph that sine function. So we've got x is a function of y and y is a function of x. But when we compute the inverse functions, we always take a restriction. We always choose to restrict ourselves to the interval from pi over 2 to pi. So let's get rid of that for a moment and restrict ourselves to the interval. I said pi over 2 to pi, negative pi over 2 to positive pi over 2. I don't know why I said pi over 2 to pi. That's not right. So there's the sine function that we take the inverse of. There's the rest of the sine function. So we say if we restrict ourselves to this interval, then we have an inverse. The whole inverse relation looks like that. And if I want, instead of an inverse relation, an inverse function, I take this restricted version of the sine function and I switch the roles of x and y. So rather than having y equals sine of x, where x is between negative pi over 2 and pi over 2, we could have x equals sine of y, where y is between negative pi over 2 and pi over 2. And we see that's what we've got. So now if I take composite functions, we should be able to get x back at least on that interval from negative pi over 2 to pi over 2. Let's actually make sure our x values are graphed in radians. And then rather than writing x equals sine of y, I'm going to start calling it g of x. Well, actually, I'll call it f inverse of x equals arc sine of x. And we see that arc sine of x and x equals sine of y, where y is between negative pi over 2 and pi over 2. Those are the same function. It's easier to see if that's out of the way. There's x equals sine of y. There's f inverse equals arc sine of x. Same thing. Basically, I'm just taking the arc sine of both sides of this, and then when I get that y by itself, I'm saying that's not my original y value. This is called f inverse. We replace that y with f inverse, and we've got that function right there. So now if I take the composition of f of x, which is y equals the sine of x, with f inverse of x, on the interval from negative pi over 2 to pi over 2, I should get x. Let's make sure that we take the restriction. I'm going to call my sine of x function f of x now. And then let's replace x with f of x and see what we get. Oops. And then replace x with f inverse of x and see what we get. Okay, it's having a problem with this for some reason. All right, let's see what it says. It says, you've defined f in more than one place. Try deleting some of the definitions of f. Okay. We're going to type that again a bit later. All right, actually, I see what happened. Okay, so I wanted f inverse of f of x. Let's see what we get. And then I wanted f of f inverse of x. You see what we get. You guys see it? You see how it's not exactly what we would expect? If we just graph y equals x looks like that. Let's graph that in green. Let's make it solid. And let's get rid of some of these graphs. It's a little bit distracting. Get rid of that one and that one and that one and that one. We've got f of x is sine of x on our restricted interval, and f inverse of x is the arcsine of x, which is defined for x between -1 and 1, and it gives us y values between -π/2 and π/2. When you compute f inverse of f of x, this is what you get. You get part of that. Now, if I substitute in the x values at the end of my domain for f of x, so f of x has this restricted domain of -π/2 to π/2. This is what we get. We'll evaluate this at -π/2. And we'll evaluate the same expression at +π/2. And let's plot some ordered pairs. Here's that green line coming from. This is what we see. So when I have f of f inverse of x, that's going to be well defined for all x in the domain of that restricted sine function. So we get x back. We get y equals x, which looks like that. But only on the interval where f of x is well defined. So only on that interval from -π/2 to π/2. Then similarly, if we look at f of f inverse of x, we're going to get pretty much the same thing, except watch that. It's still y equals x, but it's not on the same interval. And the reason that is because our f inverse graph is given by this arcsine function. And arcsine only takes values as inputs that were in the range of the original sine function. The original sine function mapped to the interval from -1 to 1, right? So that means when you take the arcsine, you can only take the arcsine of values between -1 and 1. So if I have an x value that is like π/2, well, π/2 is like 3 divided by 2, about 1.5. We can't find the arcsine of 1.5. We can't find the arcsine of π/2 because what is the arcsine of π/2? It's the angle whose sine is π/2, or the angle whose sine is approximately 1.5. And you don't get a sine of approximately 1.5, not from just a traditional sine function with an amplitude of 1. So that's not going to work. But if you just look at this f inverse function, f inverse is well defined on that interval from -1 to 1. So when I take that function that's defined on the interval from -1 to 1, and then I apply the original function f to that, we do get x back, but only for those x values for which f inverse is defined. So we would see something like this, but with the points reversed, or with the functions reversed. So we'll evaluate this at 1. Get that point. Evaluate this at -1. Get that point. And so that's what happens if you take f of f inverse and f inverse of f of x. Now, f inverse is that arcsine function. That's just the way we chose to define it. We said the original function f is going to be called sine. F inverse is the arcsine. So you might say, okay, but what if I just look at f inverse of f of x in general without this restriction on x? Well, let's think about what that function would look like. So I have my f inverse on the outside. I'm going to call it g for now. So that's my arcsine on the outside and my sine of x on the inside. Okay, whoa, isn't that pretty cool? I think it's cool. It's not just y equals x. Y equals x is this white dotted line. We do get y equals x on the interval from negative pi over 2 to pi over 2, but we get these other line segments. And the other line segments, it looks like our slope is -1 from pi over 2 to 3 pi over 2. Our slope is +1 from 3 pi over 2 to 5 pi over 2. So it repeats. And it looks a little bit like our sine function, right? Because a sine function, if we just graph the sine of x, let's graph just y equals sine of x. It looks like that. So it has kind of the same shape, except we've got these corners. So we've got this piecewise linear function. It's x on the interval from negative pi over 2 to pi over 2. And then it's negative x plus a constant. And I think that constant is going to be pi. Because if I continue drawing that line segment, it's going to intersect the y-axis at y equals pi. And then on this one, it has the graph has a slope of 1. And then if I keep drawing that line, I think I should get something that is approximately, I don't know, is that negative? It's going to be negative 2 pi, something like that, on this interval over here. But we can figure out what that is, and think about why that is the case, by thinking about like just sort of domain and range issues for this arcsine function, or arcsine of the sine of x function. Well, just a second. Okay, so let's zoom out a little bit. If we zoom out, looks like the domain is all real numbers. Looks like we've got a continuous function, and the slope is the slope of x, and then the slope of negative x, and the slope of x, and the slope of negative x. The slope is 1, -1, 1, -1, 1, -1. Of course, the y-intercepts are changing as well. And I think that's kind of interesting, but you might think, okay, well, why is that the case? Well, if we look at this original function, g of x equals arcsine of the sine of x, when we're deciding what the domain of g of x is, we are really looking at that inside function, and we say, well, what is the domain of sine of x? Well, the domain of sine of x is all real numbers. And when I take the sine of any real number, I always get a number between -1 and 1. And the arcsine is well defined for any input between -1 and 1. So this is going to work all the time. Doesn't matter what x is. Any real value of x will be fine. We'll always get a y value out. So the domain of this function, arcsine of sine of x, is all real numbers. Let me type that up. So you might ask yourself, what happens outside of that interval from negative pi over 2 to pi over 2? What if I put in an x value that is beyond that restricted domain of the original sine function? I think probably the easiest one to choose is, say, x equals 3 pi over 4. So we would be in quadrant 2 if we were drawing a reference triangle. And then we could compute the arcsine of the sine of 3 pi over 4. Let's do this on paper. So I would compute the sine of 3 pi over 4. Now, typically the way I do that is I draw some reference triangle. 3 pi over 4 is 3/4 of pi. So that reference angle is 45 degrees, or pi over 4 radians. So this is a 1, 1 square root of 2 triangle. The adjacent side has a directed length of -1, because our x's are negative over here. Our y's are positive, and of course the r is always positive. So when I compute the sine of this angle, it's just going to be opposite over hypotenuse, or 1 divided by square root of 2. We typically rationalize that, and we get square root of 2 over 2, right? And then we say, what is the arcsine of square root of 2 over 2? Now remember, whenever you compute the arcsine, you don't get angles in quadrants 2 or 3 ever. You always get your angles in quadrants 1 or 4. Because arcsine always returns values between negative pi over 2 or pi over 2. So even though our reference angle, or our angle that we started with, was 3 pi over 4, after we compute the sine of that value, then we have to take the arcsine of that, and this angle is not going to be 3 pi over 4. It's going to be the angle that has the same sine as 3 pi over 4 that lies in quadrants 1 or 2. So the sine of 3 pi over 4 is this positive value. When I'm looking at quadrants 1 and 2, I know my sine value is positive in quadrant 1. So we'll have a 1 square root of 2 triangle here. That reference angle is still 45 degrees or pi over 4 radians. And we say, well, what is the arc sine of that square root of 2 over 2? It's going to be that angle. It's going to be 45 degrees or alternatively pi over 4 radians. So at x equals 3 pi over 4, instead of getting 3 pi over 4 like we might imagine, instead of just continuing that line y equals x and continuing to go up and continuing to increase, we say, okay, instead of looking at that angle, I want to find the sine of that value and then say, okay, well, what is the arc sine of that particular value? The arc sine is positive in this quadrant, so our angle is actually pi divided by 4. So we get this. Pi over 4 is a half of pi over 2. And it starts to decrease. And at pi, we would take a sine of pi, and you'd say, well, what's the sine of pi? Sine of pi is 0, right? So we evaluate sine of pi, we get 0. And then we say, okay, well, what is the angle whose sine is 0 on the interval from negative pi over 2 to pi over 2? Now, I can't draw a triangle for 0, but I can look at the sine graph. Y equals sine of x looks like this. And we're interested in this interval from negative pi over 2 to pi over 2. We say on that interval, where is the sine value equal to 0? Well, x equals 0, of course. So this is 0. So when we have x equals pi here, instead of the arc sine of sine giving me a pi back, which is what we would expect if we could just take f inverse of f and get just x back. We're not getting x back. What we get is the arc sine of that sine value, and that sine value maps to 0 on the interval of interest. So we're always going back to that interval from negative pi over 2 to pi over 2. I think when I think of the sine function and I think about my reference triangles, I think about going around and around on that unit circle, or just going from starting at theta or theta equals 0, just letting theta increase. We go and theta can go on from 0 to infinity as it increases, or theta can start at 0 and then we can go backwards and go to negative infinity. You can go forwards or you can go backwards. But theta can be any value that you want. Any real number is fine. But whenever we take the arc sine of something, it's like somebody that keeps going back to the same region of, or that same interval of x values, instead of continuing to go in a positive direction or continuing to go in a negative direction. It says, no, I'm not interested in that. I want to go back to this interval from negative pi over 2 to pi over 2 and find my answer. So that's what happens at pi. We find the sine of pi, we get 0, then we take the arc sine of 0 and we get 0, and that gives us this value. And if we continue in this way, at 3 pi over 2, we say, okay, what is the sine of 3 pi over 2? Well, we know the sine of 3 pi over 2 is just negative 1, right? We're going to be right there at the bottom. But the arc sine of the sine of 3 pi over 2 is not 3 pi over 2 like it would be if the functions were 1 to 1. I would imagine that I would get just 3 pi over 2, and we just have that line y equals x, right? If the functions were 1 to 1, that's what we would get, but that's not what we have here. Instead, we take our sine of 3 pi over 2, we get negative 1, and then we say, okay, I'm looking for an answer, but I don't want this answer. I don't want 3 pi over 2. I'm looking for an angle whose sine is negative 1 on the interval from negative pi over 2 to pi over 2. So I go back to this interval and I say, where can I get a sine of negative 1? Well, it's at negative pi over 2. So instead of getting 3 pi over 2 from this, we get negative pi over 2 from that. And so we map to this point. And now it kind of looks like a sine function, doesn't it? We're going up and then we go back to 0, and then we go down, and then we imagine going back to 0. And that pattern's going to continue. So this was pi over 2, that was pi. This was 3 pi divided by 2. And then we might be interested in what happens at 2 pi and 5 pi divided by 2, and so on. We know at 2 pi, we're going to have a sine of 0. So if I plugged in a 2 pi here, I'd have sine of 2 pi is 0. And what's the arc sine of 0? Again, the angle whose sine is 0 on the interval from 0 to pi, or negative pi over 2 to pi over 2. And we're going to get 0 again. So we get back to that 0 point again. And then if we wanted to, we could try, multiples of pi over 4. Those are sort of my favorites. On this interval from 3 pi over 2 to 2 pi, I might try 7 pi over 4. So I'd be in quadrant 4 here. And again, I'm thinking about going 7 pi over 4 radians, starting at the positive x-axis and then going almost all the way around to quadrant 4. In that case, this is what would happen. I say, well, what's the arc sine of the sine of 7 pi over 4? Well, first I find the sine of 7 pi over 4. Well, that's a reference angle of 45 degrees. So I have a 1, 1 square root of 2 triangle. My y value is negative. My x value is positive. The r value is always positive. And so we have a sine of opposite over hypotenuse. So it's going to be negative 1 divided by square root of 2. Or if you prefer, we'll rationalize, and we have negative square root of 2 over 2. And then I say to myself, okay, I don't want that 7 pi over 4. I want an angle between negative pi over 2 and pi over 2. What is the angle between negative pi over 2 and pi over 2 that gives me that sine value? That sine value comes from x equals negative pi over 4. You might say, well, is that the same picture? It is, except I didn't get there in the same way. Instead of going from the positive x-axis and going 7 pi over 4 radians in this direction, I went negative pi over 4 radians in this direction. And that is actually the value that we would get, because our arc sine function always returns angles between that negative pi over 2 and pi over 2. So we get negative pi over 4 there, which is that point. I'd be at 7 pi over 4. I get negative pi over 4 there. And then at 9 pi over 4, then we'll be in quadrant 1 again. And so we'll have a positive square root of 2 over 2 here. And you say, well, what's the arc sine of positive square root of 2 over 2? Well, I could go all the way around. I could go around 1 revolution, then go pi over 4 units to get to 9 pi over 4. Or I could look for an answer in this interval. The answer in that interval from negative pi over 2 to pi over 2 is just that 45-degree angle, or pi over 4 radians. And we just continue in this way. At 5 pi over 2, sine is 1. So we take the arc sine of 1. Say, what is the angle whose sine is 1 on the interval from negative pi over 2 to pi over 2? It's pi over 2. And so we get this, it looks like y equals x. Looks like y equals x on that interval from negative pi over 2 to pi over 2. And then it's y equals negative x plus a constant on the interval from pi over 2 to 3 pi over 2. And then it's positive x minus a constant on the interval from 3 pi over 2 to 5 pi over 2. And that pattern continues. And we see that it looks a little bit like the sine function, in the sense that our sine function looks kind of like this. It sort of has that same behavior, but it's got these sort of weird corners on it. Now, we can actually come up with what's called a Fourier series for this function. We add infinitely many sine functions of various frequencies together, and we're actually able to sort of get the corners to come out of this. I think it's kind of cool. It's sort of beyond the scope of a Calculus 1 course, but if you're interested in it, there is some information on that Desmos graph. So I will put the link to that Desmos graph online And now we know sort of where that graph of the arc sine of x comes from. It comes from this fact that every time we're outside of the interval from negative pi over 2 to pi over 2, when we compute the sine of an angle, we get the number between -1 and 1. And then instead of just taking the arc sine of the sine of that and getting that number back, instead of getting x back, we find this value first, and then we always seek an answer to that question. Sine of what angle gives us this number on the interval from negative pi over 2 to pi over 2. So I'm thinking either with reference triangles in quadrants 4 and 1, or if I'm talking about quadrantal angles, I'm thinking about 0 and pi over 2 and negative pi over 2, like this angle and this angle and this angle from my graph of the sine function. Or if you want, you could use the unit circle as well. All of those are great ways to get the values of this arc sine function. But remember, your arc sine is always going to give you those angles between negative pi over 2 and pi over 2. So we get this cool wave. Now I want to show you the graphs of the other ones instead of not just looking at arc sine of the sine of x. Maybe we'll look at arc cosine of the cosine of x, arc tangent of the tangent of x, and so on. I just want to show you some cool graphs. And if you want, you can do an exploration like this and think about like why you're getting the values that you're getting. On the restricted domain, we'll always get y equals x, but outside of that restricted domain, we might not get y equals x. We might get something that's closely related to x, but isn't quite equal to x, because we're always seeking our answer in that restricted domain of the original function, which is the range of the inverse trig function. So that is the arc sine of the sine of x. Now let's look at the arc cosine of the cosine of x. Now remember, the domain for the cosine of x was all real numbers. So the arc cosine of the cosine of x is going to be well defined for all real numbers. But the restricted domain was 0 to pi. We just chose to restrict ourselves to the interval from 0 to pi to find the arc cosine function. So let's look at the graph of arc cosine of x now. Kind of looks the same, right? But we've shifted everything. Instead of having y equals x on the interval from negative pi over 2 to pi over 2, now we've got a graph of y equals x on the interval from 0 to pi. So if I were to plot those points, I would be plotting 0, 0, and pi, pi, instead of that negative pi over 2, negative pi over 2, pi over 2, pi over 2. Because we're talking about the cosine function. And then you say, okay, but what happens outside of the interval from 0 to pi? Again, we do that same thing. If I look at, let's say 3 pi over 4, I say, well, what's the cosine of 3 pi over 4? It's square root of 2 over 2. And then I say, what is the arc cosine of square root of 2 over 2? I say, I'm looking for the angle whose cosine is square root of 2 over 2 that lies between 0 and pi. And so instead of getting 3 pi over 4, we get, I said 3 pi over 4. 5 pi over 4, I guess, is what I should have said. Instead of looking at 5 pi over 4, instead of getting 5 pi over 4 back, I look for another angle that has the same cosine. Actually, I think I misspoke because I was thinking of 3 pi over 4. Let's look at 5 pi over 4. Sorry about that. At x equals 5 pi over 4, that's outside of the interval from 0 to pi. So we compute cosine of 5 pi over 4. And we get that negative square root of 2 over 2. And then we say, okay, well, what is the arc cosine of that negative square root of 2 over 2? Well, it is the angle whose cosine is negative square root of 2 over 2 that is on the interval from 0 to pi. Well, cosine is negative whenever x is negative. So cosine will be negative in quadrants 2 and 3. And in quadrant 2, well, that is an angle that we actually have on that interval from 0 to pi. If we're on the interval from 0 to pi, we're in either quadrant 1, that's from 0 to pi over 2, or quadrant 2, from pi over 2 to pi. So when we're in quadrant 3, we say if I want a cosine value of negative square root of 2 over 2, I've got to go back to quadrants 1 and 2 and find that x value that gives me the arc or the cosine that I want. I'm saying too much. I find myself waving my hands and not writing anything down, and that's always a bad sign. So let me write something down. So our cosine graph looks like this. We took the restriction to the interval from 0 to pi to create the arc cosine graph. So our arc cosine always returns angles between 0 and pi. So if I'm asked for the function value of arc cosine of 5 pi over 4, I don't get 5 pi over 4 back because 5 pi over 4 is outside of that interval from 0 to pi. So what do? I compute the cosine of 5 pi over 4. And if I'm using reference triangles, that means I'm in quadrant 3. So my reference angle is 45 degrees. My x value is negative here. My y value is also negative, and I've got a square root of 2 on the hypotenuse. It's a little bit difficult to see. There we go. And then I say so that's why I have that cosine value of negative square root of 2 over 2. So the adjacent over hypotenuse is that negative 1 divided by square root of 2. When we rationalize, we get that. But then we say to ourselves, okay, I don't want that angle. I don't want the angle 5 pi over 4. I want the angle that gives me the same cosine value that is on the interval from 0 to pi. So I'm looking for a reference triangle in either this quadrant or this quadrant. I don't want anything in quadrant 3 or 4. I'm not interested in this angle at all. And you say, okay, well, where is the cosine value negative? Well, between quadrants 1 and 2, cosine is positive here and negative here. So our reference triangle will be in quadrant 2 this time. And we still have a reference angle of 45 degrees. And the cosine value is still adjacent over hypotenuse, which is negative 1 divided by square root of 2. But now our angle, instead of being outside of that region, or outside of that interval from 0 to pi, is within the interval from 0 to pi. So if that reference angle is 45 degrees, this is 135 degrees, or 3/4 of pi. Sorry, my document camera is having trouble focusing. This is 3/4 of pi, so we'll get 3/4 of pi here. So when this cosine value is negative, we'll always get an angle that lies in, for this function, we will always get an angle between pi over 2 and pi. Whenever we get that negative value for that cosine function, we'll get an angle over here. Now, if the cosine is positive, then we'll get an angle between 0 and pi over 2. But as far as the input values are concerned, we can input any value we want because cosine is well defined at any real number. So you can put in any angle. It does not have to be on the interval from 0 to pi. And then you'll get a value between negative 1 and 1. And you can take the inverse cosine of that value. And because this restriction maps onto the interval from negative 1 to 1, you'll always be able to find an x value on this interval from 0 to pi that gives you the y value that you're looking for. And that's why we chose the restriction to map to the entire range in the first place. Since it maps to the entire range, we will always get an answer. It just might not be the answer that you were originally looking for, but we will get an answer. And if this value is negative, we'll get an answer in quadrant 2. If this value is positive, we'll get an answer in quadrant 1. So if we look at that, and we notice that the answers for the arc cosine graph, or the y values for the arc cosine graph, are always between 0 and pi. Let's go back to our Desmos graph. See, it looks like that. Look at the y values on the graph. Notice that the y values are all between 0 and pi. And on the interval from 0 to pi, we have the line y equals x. But outside of that interval from 0 to pi, we sort of have this sort of zigzag thing happening. And of course, it's happening the way that it's happening because on the interval from pi to 3 pi over 2, actually, let's graph the cosine function, shall we? So on the interval from pi to 3 pi over 2, our cosine values are negative, so I'm expecting an answer in quadrant 2. So I'm expecting a value that is between negative or between pi over 2 and pi. And so we get all of those values between pi over 2 and pi there. And then on the interval from 3 pi over 2 to 2 pi, our cosine is positive. So I'm expecting values between 0 and pi over 2. And so we get all of these values. And then from 2 pi to 5 pi over 2, the y values are positive. So I'm expecting values between 0 and pi over 2. And that pattern continues. So every time the cosine function is positive, we map to x values or y values between 0 and pi over 2. And every time that cosine function is negative, we map to arc cosine values between pi over 2 and pi. I hope you can see that these values at the bottom go to the top parts of these little triangles, and these values here go to the bottom parts of the triangles. And that's because the arc cosine of a positive number is between 0 and pi over 2, and the arc cosine of a negative number is between pi over 2 and pi. So that's what arc cosine looks like. I'm not going to go through all of this for every single function, but I just wanted to give you a sense of what they all look like. Arctangent of tangent of x looks like that. That's kind of cool. Looks like y equals x on the interval from negative pi over 2 to pi over 2, and then it repeats. Arc cotangent is going to be similar. Now arc cotangent always gives us values between 0 and pi, so we see that we get those values between 0 and pi now, and it looks like a whole bunch of y. Looks like y equals x, but it's repeating itself. It always has the same slope as y equals x, but of course different y-intercepts for different branches. We look at the arcsecant of the secant of x. Doesn't that look like the cosine function? The arc cosine of the cosine of x? Yeah, those are the same, aren't they? And that's because the arc cosine is defined by a restriction of the cosine graph from 0 to pi, and the secant is defined using that restriction to 0 to pi as well. I think that there might be some issues with this one though. With the arcsecant, this is only well defined when x is not an odd multiple of pi over 2. So technically, I think that this graph might be incorrect because I can't substitute any multiples of pi over 2. This function should probably have some open circles at, let's say, pi over 2 and pi over 2. Should look like that every time we're at an odd multiple of pi over 2. So we'll have something like that at pi over 2, and then the same thing at 3 pi over 2. Oops, sorry. 3 pi over 2 and pi over 2, because the range is 0 to pi. We're just talking about that, sorry. And then at 5 pi over 2, and have pretty much the same thing. Open circle again. And why do we have open circles? It's because that secant function is 1 divided by cosine, and we can't divide by 0. So we are going to have issues every time that secant is undefined and the secant is undefined at all the odd multiples of pi over 2. So that's roughly what it looks like. But of course, we would want to do that for all of the possible multiples of pi over 2. Or odd multiples of pi over 2. So we're going to see an open circle there, 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 and there, and then there would be another one there, and another one there, and then another one on the next branch, and so on and so forth. Arc cosecant and arc sine are probably very similar in the same way. We looked at arc sine to begin, right? That was arc sine. Let's look at arc cosecant. They're the same, except we should have problems every time the sine of x is 0. So this arc cosecant graph should have open circles at all of the odd or all of the multiples of pi. So at 0, we'll have 0 as an open circle. And then we'll have an open circle at pi and 0. And then we'll have an open circle at 2 pi and 0. And so on. So we can see that these graphs are very similar, arc sine of sine of x and arc cosecant of sine of x, but the arc cosecant is undefined whenever that denominator is 0. We don't have to worry about a denominator being 0 with the arc sine of the sine of x because the sine of x is giving us, or is well defined for all real numbers, and it always returns values between -1 and 1, and the arc sine is always well defined between -1 and 1. I think the only one that we didn't look at was arc cotangent. Arc cotangent looks like this. That is, our cotangent is cosine divided by sine. So we're going to have a function that is undefined whenever sine is 0. So we should have open circles at the end of each of these line segments. I hope you see that periodic nature of all of those. We don't get just x anymore when we take the inverse trig function of the original trig function. We get y equals x on that restricted domain, but outside of that restricted domain, we don't get that y equals x anymore. We always go back to that interval from our restricted domain. Now remember, the restricted domain for sine, tangent, and cosecant is -pi/2 to pi/2. So we're always going to get angles between, or in quadrants 4 and quadrant 1, quadrants 4 and 1. And then with the cosine, secant, and cotangent, we restrict ourselves to the interval from 0 to pi. So these arc cosine, arc cotangent, and what was that one? Cosecant. They're always, is it cosecant? Is that one right? Secant, actually. They're always going to give us values between 0 and pi. So that's it. We don't always get y equals x. That's the point. I think it's kind of cool. And if you're interested in coming up with some way to represent this periodic function with a sum of trig functions, we can construct what are called Fourier series. It's like an infinite sum of sine functions, or an infinite sum of cosine functions, or a linear combination of sine and cosine functions and constant functions. And it actually gives you this function everywhere the original function is continuous, and it gives us the average value of the limit from the left and the limit from the right at any jump discontinuities on the interval, or it gives us the average value of the jump discontinuities, or the average value of the limit from the left and limit from the right at each jump discontinuity. That's what this series converges to. So I think that's pretty cool. But if you're interested in that, I'm going to leave this leave this link in the description, so you can learn about Fourier series if you want to. Now it says undefined there. It's just because I redefined the function. I will fix that before I post the link.